Hi guys, in this little video, I just want to talk about the fate of pyruvate when oxygen is not present and we're in yeast and certain other bacteria. So yeast contain a slightly different fermentation pathway than eukaryotic systems do. And I'm actually really glad they do because this allows us to make ethanol. So let's show you how that happens. So pyruvate, structure of it's shown here. The first step in this process is going to be the decarboxylation of pyruvate. Okay, so here, notice carbon 1 of pyruvate. It looks almost like a carbon dioxide, and in fact, the enzyme that converts pyruvate to this molecule, acetaldehyde, this is called pyruvate decarboxylase. That's a very important enzyme for yeast, and in fact, humans and other mammalian and eukaryotic systems simply do not have the gene that will make this particular enzyme. So we don't have that, that gene. Yeast and certain other microorganisms do have this gene. Okay, so we've now converted the 3-carbon compound of pyruvate into the 2-carbon compound acetaldehyde. Next, what can happen is the interconversion of acetaldehyde into ethanol. So this is carbon 1, 2, this would be carbon 1 and 2. So now notice, look what's happening here. Here we have an aldehyde functional group at carbon 1 being converted into a primary alcohol of ethanol. So just like we saw in the previous video for eukaryotes that do lactic acid fermentation, this process is going to involve NADH being converted to NAD+. And what's happening here is that the hydride of NADH, I won't bother to draw this all out, it's exactly the same as it was in the previous video, but the hydride will react with the aldehyde and end up being right here. So it's going to attach to carbon 1 and convert the aldehyde into an alcohol. And the enzyme that performs this, this very important reaction is called alcohol dehydrogenase. You may have noticed a common theme for these enzyme names. Anytime an enzyme has the word dehydrogenase in its name, it more than likely is going to use one of these electron or hydride carriers like NADH or possibly FADH2. So keep that in mind. Again, any enzyme that has the word dehydrogenase is going to use a reducing agent like NADH or FADH2. All right, so this process now is called alcoholic fermentation. Or sometimes ethanolic fermentation. And it does involve this key enzyme. We don't have this. So this is not in eukaryotes. Too bad it's not, because if we did have that gene, we could kind of switch it on and we could actually make anytime we wanted, we could make ourselves a little ethanol. But unfortunately, we don't. So we have to rely on yeast to do this ethanolic or alcoholic fermentation for us. Last point I'll make, just like we saw in lactic acid fermentation, the production of this cytosolic NAD+ helps to replenish this pool in the cytoplasm so that glycolysis can continue. And remember, glycolysis is ultimately making more pyruvate. So even in the absence of oxygen, yeast can go through quite a bit of glycolysis and ultimately make ethanol. But the reason for that is the ability of alcohol dehydrogenase to make NAD+. All right, so that wraps up our discussion of alcoholic fermentation and I think all of the various fates of pyruvate. Good luck with everything.